Okay, let's continue our discussion of how differential equations give rise to population growth models. And in particular, this example is about half-life. So half-life, as we will discuss, is the concept of how long it takes for a material to decay to half of the amount that you originally started with. So in example 3, the half-life of the apocryphal element 42J is a fleeting 5 days. Graph the amount of 42J over the course of a month, beginning with an initial amount of 100 grams. So we start with, at time t equals 0, 100 grams. I'll put a little dot on my scatter plot. 5 days later, I should have half of that. So half of that 100, I should have a dot here at 50. Half of that again at 10 days. So half of that 50, I should be at 25 grams. And then at day 15, 5 days later, half of that 25 should be 12.5. And I just keep continuing this. I'm going to take half of that 12.5 at day 20, half of that at day 25, and just keep taking half. And you will probably notice this as, especially after I connect it, it looks suspiciously like exponential decay. So this is one of those applications, a pretty major application of exponential growth and decay that you ordinarily talk about in not just math classes like pre-cal and algebra, but also in, say, a chemistry class. Okay, so I'm going to turn it over now to an expert on Half-Life to give us a little bit of background information on it.
Hi, I'm Gordan Freeman, and I know all about Half-Life. In fact, I probably know twice as much about Half-Life than most other people. Just try to do a bit of research on Half-Life, and you will more than likely find me swinging a crowbar, wielding a gravity gun, or dealing death to headcrabs. None of that really has anything to do with Half-Life, but it's still really fun.
Indeed.
Anyway, you see, certain substances decay over time. If the decay rate is constant, it is represented by the Greek letter lambda, and the decay can be modeled exponentially as n of t equals n sub naught times the natural base to the negative lambda times time.
Gordan, what was that? Could you tell me again?
N of t equals n sub naught times the natural base to the negative lambda times time.
Okay, thank you. I didn't quite catch that the first time there.
A substance's half-life, t sub 1/2, is the amount of time it takes to decay to 1/2 of the original mass.
All right, so if we take a look at Gordan's equation here, this is very similar to our equation. This n of t would be our p part, and this n sub 0 would be our c, our initial amount. And then instead of our k here, it has a negative lambda, this Greek letter there. And that's negative just simply to indicate, of course, that this is a decay.
Let's say you have a limited edition silver crowbar made from AG111, which has a half-life of 7.45 days. This means that in about a week, your crowbar would only have 1/2 its original mass. In a fortnight, your precious crowbar would have 1/4 of its original mass. My suggestion is to get a crowbar made from steel or titanium. Those will last a bit longer.
Oh, wise words, Gordan. Wise words. Okay, so just a recap here. Half-life is the time it takes for a given amount of radioactive material to decay to half the amount that we started with. So according to physicists like Gordan Freeman there, it is not an unreasonable assumption to assume that the rate at which radioactive substances decay is directly proportional to the amount, the mass in your object. And that sounds just like our exponential growth equation for populations. It's just that this one is decaying, which means that it should have the exact same exponential growth or decay equation, y is equal to c times e to the kt. And again, this looks just like the equation that Gordan Freeman gave us, just a little bit less complicated without its little Greek letters and stuff in there. So speaking of some half-lives, here are some half-lives, and some kind of popular half-lives that sometimes come up in a problem, excuse me, like the plutonium, the 239 plutonium isotope, and we've got a half-life of 24,100 years, which means that it takes a long time for that stuff to decay to half as much as you originally started with. Another pretty popular one is this carbon-14, which is used in carbon dating. It takes an amount 5,715 years to decay to half as much as what you started with. This Nobelium here, which, whoops, wrong direction. This Nobelium, which I think it's one of those synthetics, 25 seconds for a half-life. It's barely even there. All right, so let's take a look at an example to apply this half-life concept. Suppose 10 grams of plutonium isotope Pu-239 was released in the Chernobyl nuclear accident, and you can see a picture there. It's pretty haunting. How long will it take for 10 grams to decay to 1 gram? Answer to that question, of course, is pretty long, and we'll be far, far dead, to be sure, but let's go ahead and verify that with some mathematics. So example 4 here. Example 4. So we're talking about this Pu-239, which has a half-life. This is usually the way that we write this. P sub 1/2 is equal to, and from the previous half-lives page, you can see that's the 24,100 years. A long time, right? And then it also told us, I think, in the problem that at time 0, we have an initial amount of 10 grams. And we want to know at what time do we have just 1 gram left? So that's our question here. How long is it going to take for that 10 grams to decay to have exactly 1 gram left over? All right, boop. So we're going to start this whole entire process with our exponential decay model, which is y is equal to e to the, whoops, nope, put a c in there, e to the kt power. All right, and one of the things that I'm going to go ahead and stick into my equation is my initial condition here, which was 10 grams. We know that that's supposed to be our 10, our c that's right there in the equation. So I'll rewrite that as y is equal to 10 e to the kt. And now we're going to use our half-life in order to figure out what our k value is. Our k value, which is that constant or proportionality. Okay, so I'm gonna stick in 24,100. That goes in for our time value. That goes in here. And then our y value should be half as big as what we started with. We started with 10 grams. We should end up with 5, right? So using this half-life idea, I'm going to have 5 grams when I started with 10 times e to the k times 2,000. Or there I go again. 24,100. 24,100 times k. And we're going to solve that for k. So solving that for k, you can see this whole entire problem is going to turn into just algebra. I'm going to divide the 10 over. I get 5 divided by 10. I get a half. And this always happens with these kind of equations. It doesn't matter what the initial amount is, because whatever it is, if we're talking about half-life, we're going to end up with a half as much as we started with. E to the 24,100k, got it right this time. All right, I'm going to have to take the log of both sides so that we can get rid of that exponential, as we do. So I have the natural log of a half is equal to 24,100k. And then, of course, the last step is to divide by that 24,100. So k is equal to the natural log of a half over 24,100. All right, there we got our constant proportionality, which is supposed to go in for our exponent right here. Now, here, let's think about this for a second. In Gordan Freeman's presentation, he put that exponent as a negative lambda. It should be a negative exponent. Look at what we have. We have something that doesn't look obviously like it is negative. So I'm going to use a property of exponents to, or not exponents, but logarithms, to rewrite the top of this. So I have a quotient on the inside of that, which simplifies, it expands out to the natural log of 1 minus the natural log of 2 over 24,100. And the natural log of 0, of course, no, the natural log of 1 is, of course, 0. And then I'm left with negative natural log of 2 over 24,100. And now you can see definitely that the exponent is negative. Now you may have some little formulas and stuff in chemistry if you're taking some sort of chemistry or dealing with some radioactive materials or something that you're trying to figure out half-life for. And usually you don't have this natural log of 2 in there. You have some sort of approximation for it, which is, I do believe, negative 0.693-ish over 24,100. And so that kind of formula, that number should look a little bit familiar to some of you. So I'm going to put this together to rewrite our equation. Y is equal to 10 e to the, I'm going to write it in, let's say this form, negative natural log of 2, 24, 100 times t. All right, I don't think that we're quite finished with the question, because what we want to do now is see how long it's going to take in order to decay down to just 1 gram. The 1 gram is going to go in for y, and we're going to solve that equation for t. Again, a whole bunch of algebra. So 1 gram is equal to 10 grams e to this negative natural log of 2, 24,100, solving this thing for t. So this is very similar to the steps that we just took in the previous part of this problem. Divide by 10, I got 1/10. E to this business. At this point, like if you're sick of writing this number down a whole bunch, you just leave it as a K. And I write a K. You can leave it as a K and then just remember at the very final step to put your number back in. So you're only really writing it once. And then, as we did before, we want to take the natural log of both sides of this. Boop. In order to get the natural log of 1/10 is equal to negative the natural log of 2 divided by 24,100 times t. And now I want to solve that for t. So I'm going to multiply the 24,100 up to the top and divide that negative natural log of 2 down to the bottom. So t should be equal to 24,100 times the natural log of 1/10 over negative the natural log of 2, which maybe you could just do that in your head, or you pull up a calculator. 24,100 times the natural log of 1 divided by 10. And then down here at the bottom, we've got negative the natural log of 2. And let's approximate that, of course, and we get about 80,000. All right, so I'm going to round that, 80,058 years. So yeah, I was right. At the very beginning, I said a really long time and we'd be dead, and I was totally right. So t is approximately 80,058 years. So that's how long it's going to decay to 1 gram. Let's talk about the reasonableness of this. First of all, so we know that in 24,100 years, it's supposed to decay to half the amount. So let's say we started with 10, right? And I divide that by 2, and I get, of course, 5. All right, so that's 24,100 years right there, okay? I divide that by 2. Again, let's approximate that so it gets a decimal, 2.5. I'm not quite there yet, so that's 2 times that 24,100 years, okay? And if I divide by 2 again, divide by 2, I'm at 1.25. I'm almost there, so that was 3 of them. This is going to keep happening. Divided by 2 one more time, and unfortunately, that's too small, all right? So it's someplace in between 3 times and 4 times that 24,000. So 3 times 24,100 gives us 72,000 years, but 4 times that 24,100 gives us 96. And our number of years as boop-a-doop-a-doop, 80,000 is someplace in between there, so it seems very, very reasonable. Yep, look, there you go again. Oh, another one, another one. All right, so that wraps up this particular problem on that exponential decay and half-life in particular involving Chernobyl.